then I think the limits of credits we can know some other solution in fact. What I saw is that the Yes, seems so many questions. Others of tomorrow.
Okay, welcome everyone. As part of a grand conspiracy to fill the department with my friends that will vote for me when I run for, let's say, higher office. Let me introduce Divya. I know Divya from Princeton, where we were classmates in the same batch.
I know Divya before.
Yeah. You are in this conference, that's what you're saying.
They're already occupying high office. This is on YouTube.
It's fine. I don't mind. Right? They should know who's coming for them. Okay, so let me introduce Divya. She is going to be talking about incentives and information in algorithmic economics. And over to you.
Yeah, thank you so much. Hi everyone. Thank you so much for being here. I'm Divyarthi Mohan. I am a postdoc at Boston University, and today I'll be talking about incentives and information in algorithmic economics. And I want to start with a very simple observation that our algorithmic landscape today is a complex ecosystem of strategic interactions. And this is in a big part thanks to online marketplaces and platforms like Amazon, for example, where we have buyers and sellers interacting with each other, but also interacting with their recommendation algorithm. And moreover, we have ML algorithms and AI making decisions about us in other avenues. For example, they decide whether we'll be approved for a loan or whether our resume will pass AI screening. And further, with the rapid progress in Gen AI and agentic AI, so we can have AI agents be a major player in this ecosystem, with AI agents making decisions on behalf of different stakeholders. There is going to be incentive issues arising as they interact with one another. So our algorithms now are constantly interacting with agents who have a stake in the outcome or the decision made by the algorithm. That is, algorithms are interacting with strategic agents who, for example, provide the input to the algorithm, and these agents get their own reward based on what the outcome of the algorithm is. So this means that they can game or manipulate the algorithm to get better outcomes, better rewards for themselves. And we see that, in fact, they often do. For example, Uber drivers are known to turn off their apps in order to increase search pricing. Online sellers often post fake reviews and other things to get better visibility and ranking on Amazon. And more recently, we have job seekers fine-tuning their resumes or even doing prompt injection so that they can pass AI screening. So now our algorithms need to be aware of the incentives of the agents that they're interacting with in order to perform as intended or even be able to predict the performance of the algorithms. So for a more concrete example, let me illustrate with internet ad auctions. This is a $1 trillion industry, and this is how the internet runs right now.
Should I think of all of these as repeated games? Or?
So currently, think of everything as one shot.
Okay.
Yeah, So yes, so we have internet ad auctions. For example, Google runs an auction every millisecond, right? Basically here, when a user arrives and searches for something, let's say I search from flights from Bombay to Delhi. And in that second, Google runs an auction, an algorithm that takes its input bids from advertisers and then decides what ads to recommend and what price to charge, right? So the goal of the algorithm, the platform here, is to maximize the revenue and say to increase, get good user experience, show the most relevant ads. But the agents here, the advertisers, they have their own incentives. They want to get the most exposure for the least cost possible, right? And this can be at odds with what the platform wants. So here we need tools from algorithms, game theory, and economics to design good algorithms and auctions to like perform as like what Google wants to do. So for another example, let's think of ride-sharing platforms like Uber or Ola that match like drivers to passengers. So here the platform's goal is to get the most number of successful matches and reduce waiting time, right? So they need to be making real-time decisions without even knowing how the future demand and supply might evolve, while interacting with drivers and passengers who can have their own incentives. So to tackle such issues, the field of economics and computing broadly considers two categories of problems. One is the design problem, how to design algorithms or AI systems that are robust to strategic behavior. And two is an evaluation problem. We already have algorithms and systems out there in strategic environments right now, and we want to be able to understand and evaluate their performance. And so to do that, we need to model and predict strategic behavior in these systems. And my work also roughly falls under these two categories. So the first thrust of my research is in algorithmic mechanism design. I build foundational theory in mechanism design motivated by modern applications. Here, I design algorithms that are robust to strategic behavior, that are simple and computationally efficient, while providing provable performance guarantees. And I do so especially in settings with complex informational challenges. And here, we often see that optimality is like computationally intractable or very, very complex or even just downright impossible to achieve. So here I use the lens of approximation to provide guidance on like how to design good algorithms that are robust to strategic behavior. Okay.
Divya, can you go to the previous slide?
Yeah.
So isn't this robust to strategic behavior already tackled if you design incentive compatible response, or it's for these?
No.
Or
Yes. When I say robust to
Actually-
strategic behavior, I am including designing in incentive compatible. Exactly.
Okay.
Exactly. In my mind, actually designing incentive compatible algorithms are like a really good way to do robustness.
Because all the examples you said in the very first slide, but if truth telling was the optimal option, all of those, none of those would have happened.
Correct. Yes. But sometimes, yeah, actually today I will be doing mostly like truthful options. But a lot of the examples, the reason why in real life people end up not doing truthful options is either because for that particular setting, truthful options can be a bit more complicated if you want good guarantees. And like the others are just sort of like historical reasons. Google started using generalized second price just because that is what they decided to do, and they continue doing that even though they realize that it's not truthful. Yeah. Sounds good. And the second thrust of my research is in strategic communication and learning. Here I investigate what I call the information incentive feedback loop. So what do I mean by this? So often our beliefs and preferences, and in turn the decisions that we make, are shaped by the information that we learn from each other. So this means that there's also incentives in what we communicate and who we communicate with. So my work like studies and models communication to understand phenomena such as information cascades and echo chambers. So this is not going to be the focus of my talk today, but I want you to remember that like information exchanges like shape our beliefs and preferences as we go more in detail about my work in algorithmic mechanism design. Okay, so today I will be talking about my recent work in rethinking information in mechanism design. And and before that, again, this is a snapshot of my research. My background is in theoretical computer science and algorithms, but I'm captivated by like solving problems that are motivated with like some real world issues that have to do with incentives. And here I like model these things rigorously and use like mathematical methodology and like my approximation algorithms training to provide like fundamental insights for these problems. And today I'm going to focus on, as I said, some recent work that I've been doing in rethinking information and mechanism design. Here is a quick overview of the talk. I'll start with a quick primer on mechanism design basics to just talk about how to handle incentive challenges in algorithmic design. And then I want to talk more about how my work goes beyond standard assumptions that are in these classic results and how I take on additional information challenges such as partial information into different values and like online decision making with uncertain future. Okay. So let's rethink information in mechanism design. To start with the basics, I'm going to use the single item auction as an example to talk about what is mechanism design. In fact, for the entire of the talk, almost for all of the talk, I will be only focusing on the single item case. So here I have an item that I want to like allocate, I want to like sell. And I have some buyers who are interested in this item who have their own values for the item. And my goal is just to allocate the item to the person with the highest value. That is my objective. So more concretely, you can think of it as here we have a mechanism or an algorithm. Think of it as an algorithm that takes as input the values of the agents and finds an output, which is an allocation. Who gets the item and also a payment. What price are we going to charge them? Okay. So the objective of the algorithm is to maximize what I'm going to call the social welfare. I want to find an allocation that maximizes the value of the allocation. Okay. So as I've stated like this is algorithmically trivial, right? All I have to do is to give the item to the person with the highest value. Here it's agent 2.
Sorry, but I don't understand, sir. Why not give it to the highest value person, the whole thing?
Exactly, that's what I'm saying. Like, as I've said it is trivial. All you have to do is to give it to the person with the highest value, right? And you don't even need to care about payments. Just charge them 0. Like, I have not like that. So what is the catch here? The problem is that these values are coming from agents who are going to provide the value as input to the algorithm and who have a stake in the outcome of the algorithm, right? So these agents want to win the item. They are going to get some utility. If they get allocated if they get an allocation, they're going to get that value VI minus some price that they need to pay. Okay, so the algorithm is facing an incentive challenge because each agent I has a value that is private to them, and the algorithm has to rely on the agents to provide the input to the algorithm, and they want to maximize their own utility while the algorithm has a different objective, which is to maximize the overall social welfare. Yeah.
So sorry, you're thinking of indivisible items here? Like this?
It doesn't matter. You can think of it as an indivisible item. Just think of the allocation as being 1 and zeros. Like there's going to be 1 and zeros. Yeah, it does not matter. Yeah, but it can be more general.
And here the VIs are their private values, and this may not be what they report to the mechanism.
Exactly. So these VIs are private to the agent. I have to rely on them to report something, so they can report anything they want. So exactly. So the trivial solution that I suggested is going to fail miserably because everyone's just going to think about how can I misreport the highest number possible. We are all just going to figure out how to report infinitely, right? Because they're going to get the item if they report the highest value at 0 price. So we want to design algorithms that are robust to such strategic behavior, and we'll be looking at truthfulness as what we want to now ensure truthfulness to get that robustness. So what is a truthful mechanism? The mechanism will ensure that each agent's utility is going to be maximized by reporting their true values. So nobody has an incentive to misreport a different value. Okay? So in a truthful auction, every agent I is going to actually report their true value. And it turns out in this like fundamental setting, there is a very simple and elegant solution. This is a seminal work by Divyarthi showing that the second price auction is both truthful and gets optimal welfare. So what is the second price auction? We are going to give it to the person with the highest value, and then we are going to charge them the second highest reported value as the price. So in our example here, agent 2 has the highest value. So we are gonna, and they'll report that because the second price auction is truthful, but we're gonna charge her the second highest price, which is 50. Okay, so agent 2 now has a utility, for example, of like 100 minus 50, that 50 is their payment. And it turns out they have no incentive to misreport their value, and so neither do other agents. So this is a truthful auction, and since we always allocate to the person with the highest reported value, we are also truly allocating to the person with the actual highest value, and it gets optimal welfare. Okay, and it turns out that like we actually completely understand how to design truthful mechanisms in this fundamental setting of single item auctions. But what I want to point out is that there are like some really important assumptions that are driving these classic Nobel Prize winning results. And to illustrate this assumption, I want us to think about how we would bid in an auction for this painting.
Wait, can I?
Yeah.
This has always bothered me. So this seems like the point of view, very capitalist or whatever point of view, where basically one assumes, as you said, the algorithm's only job is to do social welfare, foregoing its own profit.
That is, I also have work on revenue maximization, and that's why I had this other line before. So this one is not even about social welfare. Any sort of objective you want, I know whether or not such an allocation can be made truthful. What are the allocations that can be made truthful? If you, since you're interested, basically only allocations that are monotone in the reported value can ever be made truthful. So we actually know how to do revenue maximization with a very, very simple price that you have from like prior distribution and stuff. So I don't want to get too much into details, but people also study other objectives as revenue maximization. But in this talk, I'm going to be looking at social welfare. Yeah.
Do these ideas also work in like bounded rationality sort of thing?
Okay, cool. So I'm not going to be thinking about bounded rationality. There's many different ways to think about bounded rationality. And one way people think about is like people don't understand their own utility and have different sort of averseness and are not thinking about what other people are doing. I don't want to think about all of these things. Actually, one of the reasons why truthfulness is a really powerful like sort of robustness to strategic behavior is that you don't need to think about all these other things of like, okay, what will the other person do, and hence I will do this. Like that requires even more rational thinking. But truthfulness sort of like just ensures you that like, hey, you don't need to overthink. Just report your values truthfully. Sort of stuff. Yeah.
If agents trust the analysis.
Good. Yeah. So that is a different problem. So here it's like I am committing to the algorithm. This is the algorithm. But even there, actually, since you mentioned bounded rationality, one other notion of truthfulness is like it strengthens this more, saying that like not only is my utility maximized, it's like it's obvious to me that my utility is maximized. So that's obvious strategic truthfulness, which I'm not going to talk about today. Yeah. Cool. So yeah, so to highlight some like really strong assumptions that are like driving these classic results, I want us to think about how we would bid in an auction for this item. Like what is our value? Okay, so what do you think? I like it. I think it's a cool abstract painting, has like nice bold colors. I think I might be willing to pay like 10,000 rupees for it. And the first agent here is kind of like me, does not know anything about abstract art, and is willing to pay say 10,000 rupees for like on a first look is willing to pay 10,000 rupees for it. She's just here, but like she doesn't know anything about abstract art, but like she wants to buy something for the new like department building. Like clearly TIFR cares a lot about art. So I did not plan this for TIFR, by the way. So her job is to get a good impressive painting for like the new like department building. So she wants to do a good job, but she looks at this, thinks it's cool, is willing to pay 10,000 rupees. She goes with her art expert friend, who's the second agent. But she's just there to buy a painting for her house. Okay, low stakes. She's just there to buy some painting for her house. But she looks at this painting and recognizes the artist and says that, oh, I'm actually willing to pay up to like 5 lakhs for this. Okay. So I don't know about you, like for me and for the first agent, knowing that my art expert friend who just wants to buy something for the house is willing to pay 5 lakhs means that this is actually by some legit influential artist, right? So if I get this for the department, it would indeed be very impressive. So I am willing to actually pay even more, like 6 lakhs, so that I can win the item. Okay? And it turns out that 6 lakhs would be a steal. And I don't know if I feel like TFR is probably the only place where people might recognize the artist. Get out of the building, like elevator now, you will see a big art by V.S. Kaitan. Again, I did not plan this, okay? But yeah, as I said, 6 lakhs would be a steal. It went for like 21 crores just last month, okay? So our first agent would be super happy to pay 6 lakhs. Yeah. Anyway, what is the point that I'm trying to illustrate here? Is that we often don't even know our own value for an outcome, for an item a priori, because our values can depend on private information that other agents have. Right? So we have this challenge of partial information and interdependence that is completely missing from these classic results that we saw. And this challenge of partial information and interdependence is prevalent all around us. For example, in ad auctions, you can think of how like my value for an ad slot can depend on like a competitor's like cookies and data that they have about the target user audience, right? So to tackle this pervasive challenge, we are going to turn to the celebrated model introduced by Milgram Weber, building upon works on Wilson. In fact, Milgram and Wilson won the 2020 economics Nobel Prize in part for this contribution. So in the interdependent values model, again, I'm going to just think about the single item option. We have an item and agents. Now each agent I does not just automatically know what their value for the item is. They instead have some partial information, what I'm going to call a signal. Okay, so they privately know some partial information about the item. You can think of this as like, oh, who is this artist? Is this by an influential artist, or this is AI generated? Or even like this partial information can just also capture how much you intrinsically like it. What is your score for the item? But they also have a known valuation function, VI, that aggregates the information of all the agents to a value for the item. So agent I's value can depend on the private partial information that all the agents have. Okay? So this sort of like framework and like abstraction has been super crucial to capture a lot of different settings. And for an example, think about a resale model where my value for an item is not just dependent on like how much I like it. So SI is my partial information about it, but it can also depend on like the weighted average of how other people like it, right? Because this captures the resale potential for the item, so that shapes how much I truly value the item. And following their influential work, like there's been a long line of literature, both in economics and computer science, studying like how to design truthful auctions with interdependent values. And I want to highlight like two results quickly. One is that this is indeed a more challenging setting. Like you can no longer guarantee that like a simple second price auction can get truthful and optimal welfare. In fact, like you cannot always guarantee that you can get optimal welfare truthfully unless you make some really strong assumptions. But the second one is, in the past sort of 5 to 10 years, computer scientists have brought in the lens of approximation and have provided truthful auctions that get approximately optimal welfare in like a large class of valuation functions. But the main thing I want to say here is that all of these works make two crucial assumptions about the information structure of what the algorithm has. So one, yeah. Interdependent values. Yeah, it's interdependent values. Yeah. Cool. So what are the two assumptions that are driving these lines of work? One is that the input is given upfront. It's given all at once to the algorithm, right? So the algorithm knows all the bidders can get all their values and signals and then do the allocation and payment. And we saw that this is not often the case. We need to be making real-time decisions without not knowing the future. And the second assumption that's driving all these results is also that the valuation functions are publicly known. So the algorithm or the auctioneer knows how you would value the item knowing all the signals. That is like, why would I assume how you would value that painting even if you knew like that it was by V.S. Gaitonde? But these are two important assumptions that have been present in all of the literature in interdependent values. And my work has been to go beyond these unrealistic assumptions and take on these two additional challenges. The first challenge that I tackle is online decision making with uncertain future. So now the algorithm is only going to see the agents one at a time and needs to make a decision without knowing what the other agents in the future are going to say. And the second challenge that I tackle is in the setting where the algorithm knows nothing. The algorithm not only has to rely on the agents to report their signals, which are private to them, the agents now also have to report their valuation functions. The algorithm does not know the valuation functions a priori. And my work provides the first constant factor approximations in both of these settings. And today I will be talking mainly about the first challenge, and I will briefly touch upon the second challenge at the end.
When you say the input, you mean this private signal?
Good. So yes, now I mean the private signal. Yeah. We will see a more formal model of that soon. Okay. So yeah. So we will be talking about online decision making with interdependent values. Again, as I said, we are going to be handling two kinds of informational challenges here. First is the challenge of partial information interdependence that we saw earlier. The second is that the agents are going to be arriving online. I need to make decisions without knowing the future. And online decision making basically has this simple question at the crux, right? Should we select the current option or should we wait and gamble for something better in the future? So for example, if I have this painting for sale and I know that there are 4 buyers who are interested in this painting, but when each buyer arrives, I need to make a decision whether I'm going to give this buyer the painting or not. So maybe the first buyer arrives and is willing to pay 10 rupees for it and I think it's too low, so I say no. Once I say no, they're gone forever. I cannot go back and give it back to them. I cannot take back my decision. So now the second buyer arrives, is only willing to pay 6, it's too low, so I reject them. I cannot go back to the first person. So I move on and I see a third buyer who's willing to pay 8, and maybe now I think, okay, maybe I should cut my losses short. I'll accept this agent. But it turns out that if I had waited, there is going to be someone way better in the future. But I had to make this decision without knowing what the future was. Right? And this there's a long line of literature handling this challenging task of making online decisions. There's a huge literature on online selection problems, for example, studying different kinds of literature different generalization going beyond the single choice. And my work bridges this rich literature on online selection with this influential work on mechanism design with interdependent values to ask a very fundamental question. So given a sequence of n agents with interdependent values arriving online, and upon arrival of each agent I need to decide whether to accept this current agent or irrevocably reject them and move on to see the next one. And when I do this, I want to make sure that I can maximize the value of the accepted agent. So that is going to be my.
So do we believe the agents are in collusion or
no. So no. There is no collusion. Nobody is colluding at all. Everybody is selfish. So that is yeah. In fact, we will also look at the case where agents are non-strategic at all. They are not even strategic. So
algorithm only knows n at the moment.
The moment, but actually no. Let me make the model more clear. Yeah, we'll see the model. Yeah. So the algorithm knows n, and because we are now in this interdependent value setting. So again, what is the interdependent values? Each agent I is going to have a partial information, private signal Si, and a publicly known valuation function Pi. So I am actually going to think of the valuation functions as being known a priori to the algorithm for now. And so we're going to see these agents in a sequence. So when agent I arrives, that's when we see her signal Si. So before that, we did not know her signal Si. And we need to make a decision now, knowing the signal Si and all the valuation functions, whether we're going to accept her. If we reject her, then we go on to the next agent and we see what agent I plus 1's signal is. Okay? And you might already recognize that like if I don't make any more additional assumptions on this, even without things being interdependent, no online algorithm can like provide you worst case guarantees compared to the offline algorithm. So I'm going to look at two very fundamental models studied in online selection problems, which is the profit setting and the secretary setting. So what is the profit setting? So here we are going to have some prior distributional assumptions. Like we are going to say that like these signals, these agents, I don't know who they are. I don't know what their signal is going to be, but I know that this is the population from which they are going to come from. So the signal Si is going to be drawn from a known distribution Di, like, and each of these signals are going to be drawn independent. Okay, but the arrival order of the agents is decided by some adversary, some fixed worst case order. Okay, so this is the profit model. The secretary model, on the other hand, has the challenges sort of like flipped. So here the signals can be arbitrary. I have no prior information about where the signals are coming from. They can be adversarially chosen. But the arrival order of the agents is going to be uniformly at random. We are guaranteed that the agents are going to arrive in a uniformly random order. Okay? So like our work tackles both of these settings, and the goal here is to compete with the hindsight optimal. I want to design a good online algorithm that is able to compete with this benchmark, that knows all the signals in advance and is able to choose the max value given the signal realization.
So when you say this arrival on plus perfect setting, so the order is chosen adversarially but without knowing the signals.
Correct. Yes. Order is chosen.
Like, independently drawing at random, right? How does it matter?
So it matters because, okay, the actual profit setting, you're going to have values being drawn at, independently. Now my values are not independent. My values can be correlated. The signals are independent.
Meaning as a valuation.
So the valuation function of each agent I, along with all the signal realizations, is what dictates the value of an agent. So in the usual profit setting that most people study, all the values are independent from one another. In fact, it's one of the main things that people think about is how to handle correlated values in profits. And like our work actually provides a way to think about correlation in profits through this lens of interdependence.
So the arrival order, the person, the adversary knows the valuation.
The adversary knows the valuation, the adversary knows the distribution, but does not know the signal realization. Yeah. And I am also going to know what the order is before I start making decisions. That is also
The algorithm.
the algorithm. The algorithm knows the fixed arrival order, but that arrival order was chosen by some adversary. Yeah.
Is there a connection between them? Is one easier or harder than the other?
So there is no connection between them. Like you cannot really sort of, one thing does not imply the other. They are really like sort of like different challenges. Like anecdotally in this model, I find the secretary problem easier than the profit problem, and I'll actually talk more about the profit problem today. I'm not going to be talking about the secretary algorithm much. And it's kind of like harder for this reason that the adversary gets to choose the order. Actually, we are going to see that exactly now. So I'm going to talk about the profit setting again. Just a recall, here we are going to know that the signals are being drawn from a known distribution Di, but the arrival order can be worst case. Okay. So I'm going to start with some bad news. This is our first result. In the profit setting, even when the valuation functions are nice, like basically that means I will explain what that is later. But even when the valuation functions are nice, even when the agents are non-strategic, no online algorithm can guarantee better than an omega n approximation compared to the offline optimal. Okay. And in fact, like the counter example for this is like very clean. So I want to show you the whole proof today. But the main idea behind it is that the adversary can hide the most informative signal at the end. The adversary chooses the order. So the adversary knows who the art expert is, and that everybody only cares about the art expert and can make sure the art expert comes at the end and the online algorithm learns nothing. Okay, and that is actually what is the idea behind this counter example. So we are going to have signal Sn, which is the adversary, like the nth agency, will be drawn randomly from this known distribution uniform 0, 1. Okay, but the valuation function of each agent Vi only depends on this signal Sn. So you can think of every other signal as being deterministically 0, and we don't even care. So Vi is going to be equal to 2 to the I if and only if signal Sn is at least greater than 1 minus 1 over 2 to the I. Okay, so when Sn is above this threshold, agent I's value is equal to 2 to the I, otherwise it's 0. So note that the expected value of each agent I is just 1, right? With probability 1 over 2 to the I, Sn crosses this threshold, and that's when you get value 2 to the I, otherwise you get 0. So the expected value of every agent is 1. But for a given signal realization, if Sn is between, let's say, 1 minus 1 over 2 to the k and 1 minus 1 over 2 to the k plus 1, like the true underlying values of my instance is that the agents will have values 2, 2 square, like this geometric series up to 2 to the k, and then suddenly it becomes 0 and stays 0 forever. Right? That is the true underlying values, like for this instance. But the online algorithm has no idea, right? The only thing the online algorithm knows until it rejects everybody and sees the last agent is the only thing the online algorithm knows is that everybody's valuation has expected value 1. Every agent has expected value 1. So the online algorithm is essentially all it can do is blindly guess where to stop, or like always choose the last agent or something. But no matter who we accept, they are going to have in expectation value 1. Right? But the offline algorithm, the hindsight optimal, that gets to see the signal realization and then go and choose the max value, is going to be able to get order n over, like roughly n over 2. So with probability like 1 over 2 to the I or 2 to the I plus 1 roughly, we see that the Sn is between these two things, and whenever the signal lies between these two values, the offline optimal will choose the optimal value, which is 2 to the I, choose the ith agent. So there is this end gap between what any online algorithm can guarantee and what the best offline algorithm can get. Right? And as I said, and this is true even when the agents are non-strategic. I have not said anything about strategic agents currently. So the main challenge here comes because adversary gets to hide the information at the end, and the fact that the agents actually care about this information, right? So these agents are far-sighted. They actually care about their valuation function is affected by the agents who haven't arrived so far, who they have not even seen. Their valuation functions can depend on all signals, including agents in the future. And this makes sense in a lot of settings of interest, obviously. Like when you think of these items as being some sort of long-term investment, or like we're thinking about resale potential, you do want to think about agents having like far-sighted values. But in many settings, we can also think about agents who have myopic values, and this impossibility result has made us think about these two distinctions more carefully. So myopic agents only care about the information that they have so far. So when agent I arrives, their value is only going to depend on the signals S1 through Si and not on the future agents, because they have no idea who these agents are. And think about how we often make decisions about this, right? Like when we see reviews, we see past reviews, and that can shape our values, but not on some hypothetical future agent. So we're going to make these two distinctions, and we're going to look at agents who have myopic values. So that means that the valuation function of the ith agent only depends on the signals S1 through Si. And by making this distinction, we are able to now get a constant approximation with an online algorithm in the profit setting. And if you also take on the additional challenge of strategic agents, we can get a truthful mechanism that looks with the additional factor 2 for a large class of valuation functions that are subadditive over the signals. And for the secretary algorithm, as I said, I'm not going to talk more about it, but like just to briefly say that when I say it's slightly easier in the sense, being farsighted and myopic no longer matters in the secondary algorithm. For both of those settings, you can get a constant approximation.
Since there's like a factor 2 in going from non-strategic to truthful, is that like a black box conversion or is this
Good. So it's little bit black box, but not exactly, not really. It's actually not black box. I have to do something slightly different. I have to do something less sophisticated. So we will see that. I'll briefly mention that maybe. Yeah.
So what is truthful mean here? It's like the signal that they actually have. Do
Yes.
they reveal it or not?
Exactly. So when I come, I have an incentive to misreport my signal because the signal is private to me. So
Affiliation functions are fixed.
Yeah. We are in the standard interdependent value setting. The valuation functions are fixed.
Okay.
So in the profit model, think of it as the valuation functions are fixed and I even know all of it.
Okay.
But when each agent I arrives, they get to misreport their signals in the strategic setting.
Okay.
Yeah.
The counterexample works sort of like the Gaitonde case in which I do not know if I have to think of the valuation in terms in thousands, lakhs, or crores. Suppose I put a bound on this, then would you get such a
I can get a counterexample that where everything is
You anyway
bounded.
can't get more than the bound, right? So you will get the worst thing.
So I can actually generate other counterexamples that are like more in the boundary region, like let's say 0, 1. Like I won't know where the 1 is hiding.
Okay.
I chose to do the more
Okay.
sort of like our expert model.
Okay.
Yeah.
If you bound it away from 0 or something, let's say the values are again.
Okay, now I don't know because then I feel like you can really get stuff. No, I am not thinking about like so much restriction. I'm still trying to keep my valuation sort of like more general. If you fully bound it, maybe then maybe you can get something trivial, but that depends. I don't want to say something. Context there. Yeah. Cool. So as I said, this holds for subadditive valuation functions. So let me quickly explain what I mean by that. So like as you know, like maybe a lot of us know subadditive valuation functions from like combinatorial optimization and etc. functions. So here we are going to think about valuations as being subadditive over signals. So essentially, the signals are all complements. If my value, like knowing that you thought it was a Gaitonde and like Raghuvansh thought it was a Gaitonde, separately was like still 6 lakhs. When two of you come together and say that, oh, this is ABS Gaitonde, it's not going to suddenly make my value like 12 lakhs. So that is basically what subadditive valuations mean. So more concretely, my valuation V, the function V is subadditive if looking at all the signals S1 through Sn, my value is less than or equal to the sum of the parts. So my value only when I look at parts of the signals and zero out everything, plus my value when I only look at the complementary signals and zero out signals percent. Okay, so subadditive valuations are of course in the largest class of complementary valuations, and like they've been like super important in like. Yeah.
Is it equivalent? So usually it's written as any sum here. S is a real vector. So
so you can do it a bit differently also, but this is like a more like I'm putting less restrictions sort of. I'm asking for less. Yeah. I'm asking for less. Yeah.
the difference being is
So you could
an
say-
arbitrary sum and
Yeah.
So this is sort of like so this is basically looking at
X and
A
X.
and X complement, right? Like I'm not just looking at like but like we don't need it. So this is the version that I'm going to say. And for example, subadditive is like strictly more general than submodular over signals, which was actually very key in getting sort of constant vector approximation and truthful options and interdependent values, for which like some people want the PC West paper in 29. So for subadditive over signals, we are now going to give good news finally. So when agents are myopic, so in the profit setting with myopic agents, we have a simple online algorithm that can guarantee a 4 approximation to the expected hindsight optimum. Okay, and when I say simple, this is for non-strategic agents. When I say simple, it really is almost like the most simplest algorithm you can think of for profit settings. So the standard sort of classic algorithm that basically every profit paper that you would see will have is threshold algorithms. So you're going to define a threshold x, which is equal to like half of the expected hindsight optimal. Okay. And then you're going to look at people one at a time and accept the first person whose value is greater than the threshold. Note that since my valuations are myopic, when I see agent T, I know their whole value. That is, and I'm going to check whether they cross the threshold. But unfortunately, this fails for us because we are in the interdependent value setting. And it fails for like sort of like a couple of different reasons. One is that there can be really strong positive correlations that are happening, right? Like I can maybe the art expert is in the front and knowing their value makes all of our values come up very high. So, but like somebody's crossing threshold could mean that someone behind, someone in the future is going to have a way higher value. So there can be positive correlations because things are interdependent. And in fact, this is actually one of those very big challenges in profit settings. We know that arbitrary correlations are like impossible. You cannot get better than n lower bounds when you have arbitrary correlations. So, but what is the other thing that this algorithm is missing? Or like what is one obvious thing that this algorithm is missing? Is that like when I see that someone is obviously better in the future, I should not give it to the current agent just because they crossed the threshold. What do I mean by that? Like I have seen the signals S1 to ST so far. I know the valuation functions of the signals, valuation functions of the agents in the future. So if I see someone, I don't even know the future signals yet. So maybe their valuation could be even higher. But even just looking at the current signals, their value is obviously better than the current agent's value. I should not like accept the current agent, and I should. It's like strictly better. It's just a strictly better thing for the algorithm to wait for someone better in the future, right? And it turns out just making this additional check is enough to guarantee our constant approximation. So now I'm going to modify the threshold algorithm. I'm going to check whether the current agent crosses the threshold. But even if they cross the threshold, I'm going to check that nobody better in the future, only looking at the information so far, is obviously better. So looking at the information so far, the current agent's value is better than all the agents in the future. Yeah.
So maybe so when we say the valuation, I mean right now, so that ST, it means that we don't know the actual signals that are going to come in the future. So it's just like an expectation over.
Good. So I'm actually thinking of the worst case. It's not even an expectation. So when I say VI of ST, I'm zeroing out everybody else in the future, or like taking the worst possible realization that could happen in the future. So this is my lowest estimate of what VI could be. VI could be way better. But all I'm asking is that the current agent at least is better than the lowest possible value VI can have. Yeah.
Just trying to understand.
Sorry?
No. So I was just trying to look for something much simpler. Suppose the valuation was just the signal.
Good.
What happens in that setting?
Yes, that is the actual profit setting. That is, we know how to do it. For that, you don't need any of these things. That's only this. And in fact, if the valuation is just the signal, if the second thing will trivially be satisfied.
Yeah.
Right? So it's only the threshold algorithm, and that's just the classic profit threshold algorithm. So if my instance, so I am trying to create something that thinks about interdependence, but if it happens that we have no interdependence, everybody's valuation is just their own signal and does not depend on anybody else's signal, then we actually like go back to the setting, the algorithm itself becomes the usual algorithm and we lose no additional factors.
So here, this is like the way should it be that I'm thinking about it as saying that the fact that there are a few people who reported certain values so far might affect someone in the future enough that even in the worst case, they are probably going to give me better than.
Exactly. That is all I'm trying to say. Yes. We've seen some information so far. Even just with this, if someone in the worst case is already better, I should obviously wait for them. That it's strictly a better thing to do.
Oh.
Yeah.
So the classic threshold algorithm is clear, you will see at some point step this way. Here, why are you guaranteed? Algorithm just keep waiting,
Yes,
hoping for a good
that
value.
is going to happen. And I'm not going to show you the analysis today, unfortunately, but that is exactly the thing that you're trying to balance. That, like, in fact, so even the classic threshold algorithm, I want to nitpick that, like, you don't always stop. That's actually the biggest problem. That's why you lose if you always stop, then you don't
No,
have
because
the problem.
you know it is max of the threshold is half the expected value. Therefore, there will be a
It's expected value. It's expected value.
Okay, fair.
It's expected value.
Okay.
So even the classic threshold algorithm may not stop. You want to make sure that it stops often enough, but not too often. That's the biggest problem. And even for us, it's kind of the similar tension. You need to handle the fact that, like, so whenever we accept, we are good. We are actually guaranteed to get half of the off. The problem happens when we don't accept. Yeah, but I don't want to get into the analysis right now. Yeah. So this is, yeah.
So where are you using survival?
Good. So I'm using subjectivity to sort of say that this thing that I did, that even in the worst case, I was doing, like, all I have to do is to check whether in the worst case nobody's better in the future, is somehow good for subjectivity. Subjectivity will let me sort of get away with doing this, even though I don't know their whole value, right? I don't know that, like, what this person's true value is. It could be much higher, but subjectivity ensures that it's not going to be too much higher. Like, yeah.
So this is a lower bound on because of subjectivity. The actual bound is di of si for I being
Exactly. Yeah. Exactly.
Something else.
This is a lower bound, and the subjectivity is going to help me sort of, yeah. Yeah, I can chat about the analysis offline, but, like, I'm going to skip that for now. Yeah. Cool. And all of this was for non-strategic agents. Like, agent I comes or agent 3 comes and is willing to reveal what their signal ST is. But remember that in the strategy, like, these signals are private to the agent. So agent I can misreport their signal SI. And know that when they misreport their signal SI, it's not only affecting how much their value is, it's going to affect how much other people's values are. So, yeah, how can we, like, now make this algorithm, is this algorithm truthful, or can this be made truthful with some payments? Unfortunately, the fact that my signal can affect other people's values is crucially going to hinder this from becoming truthful. Particularly, the second step that I am doing, where I'm going to use the information so far to check whether my value is greater than everybody else in the future, cannot be implemented, because it could be that by increasing my signal ST, your value can increase so high, and I want to lie about it. But no worries. We basically turn to the power of randomization to do a small trick, and we end up losing an additional factor 2 because of that. But yeah, so the main takeaway here is that, like, to summarize, with subjective algorithms in the myopic setting, in the profit model, we get a 4 approximation when agents are non-strategic, which is a factor 2 away from the classic profit results where we have independent private values. And if you also want to handle strategic agents, we only lose an additional factor 2. And similarly, in secretary problems, here you don't need to think about far-sighted and myopic. We again lose this additional factor 2 due to interdependent values. In the classic secretary model, where the values are fixed and that have nothing to do with each other, we know that E is tight. The main takeaway here that I want you to have is that interdependence in online decision making can have strong impossibilities, like we saw. But, like, by identifying this nice class evaluation functions, when the information is complementary, we can qualitatively match the results of the standard setting. And in fact, we can do so in settings much beyond the single item auction or the single choice secretary that I told you. In a follow-up paper, we handle, like, more complex settings with combinatorial allocations. You have multiple items and you can allocate subset of items to each agent as they arrive online. And so our work, like, sort of bridges this gap between interdependent values and secretary problems in this sort of, like, more complex extensions that people have studied. And here we know that like prior work, as I said, the secretary setting with single choice has a type E approximation, and we know that it can be sort of extended all the way to like handle like valuation functions that are XOVers, that are fractionally separated. And my work not only provides constant factor approximations for a single item setting and shows that actually you can extend in a very similar fashion without losing any factor in the approximation ratios compared to the single item. I can recover the same story for online combinatorial allocations and secretaries with interdependent values. And that's what I wanted to say about the first challenge that my work tackles of online decision making in the interdependent value setting. I want to briefly talk about the second challenge, which is that now the algorithm knows nothing. We have partial information and interdependence, but the algorithm needs to incentivize the agent to also report the valuation functions and not just the signals. So here it turns out it's a much more challenging settings where like in previously, as I said, you cannot always guarantee that the truthful auction can get optimal welfare, but if you make really strong assumptions, you can get that. But those strong assumptions are not just strong and unrealistic, they become useless if you stop making the assumption that the valuation functions are known to the algorithm. But like people have also thought about like how can we look at these class of complementary valuations like submodularity, where we know constant approximation in the case where the valuation functions are public. Can we recover something like that? Is a constant approximation possible when the valuation function is unknown to the algorithm? And this is exactly the challenge that we tackle. We show that it is indeed possible. We provide the first constant approximation, and we show that a truthful auction exists that gets a phi approximation to the optimal welfare when the valuation functions are also private to the agents and they are submodular over signals. Again, the main takeaway that I want you to have is that like this challenge of like unknown interdependence can lead to even stronger impossibilities. But by identifying this nice large class of valuations when information is complement free, we can qualitatively match the results of the standard interdependent value setting. And that is what I wanted to talk about today. So a quick summary: incentives are important in algorithm design, but there are lots of like standard assumptions on it, and my work goes beyond these standard assumptions and takes on additional informational challenges. And unsurprisingly, we have strong impossibility results here in general, but we can still recover results qualitatively in really fundamental settings. And we do so by identifying useful and natural forms of information and interdependence. And that basically raises the question of like what other forms of information and interdependence we should be thinking about. And also, I would suggest you to take your favorite like optimization problem or online stochastic problem and study it under interdependent values and take on this additional challenge. And yeah, so that was my research so far. A quick word about like what I want to do going forward. I aim to build a deeper understanding of strategic behavior and various algorithmic settings. And for this, my research goal has two parts. One is again continue pushing the frontiers of like foundational algorithmic economics, especially by building upon this recent agenda that I'm driving of like rethinking assumptions on information structure. So here I want to point out a couple of directions. One is that partial information and interdependence is like prevalent in many different settings, like well beyond options, right? But mechanism design for interdependent values has been super underdeveloped beyond options. And my work, for example, studies the canonical setting of like public projects and provides like possibilities and impossibilities results and like truthful auctions, truthful mechanisms there. And there's been other works by the other people on like bilateral trade and trade division, but there's many other things to do, many other settings and many other objectives to take on, and I'm excited to tackle those. For example, I've been recently thinking about how to design contracts that will like incentivize strategic agents to act even though there's partial information and interdependence. And here are some sort of like, I just wanted to flash like some very quick next steps in the interdependent values settings that I was talking about, more close to the work that I talked about today. And a second way that I want to, like, I'm recently rethinking information is to think about how to design algorithms and mechanisms when we have predictions. So instead of assuming some sort of like knowledge about prior distributions, how can we harness side information that we get through, like, let's say some ML model where like we don't fully know how good the prediction is going to be. And here I've been like thinking about like designing again truthful mechanisms when you have these sort of like side information. Cool. And the second part of my research goal is to sort of bring in my expertise in tackling incentive issues to other domain specific problems. And here I've been like thinking recently about a few areas like data sharing and collaborative learning, but I'm like looking forward to build collaborations to tackle incentive issues in these areas like collaborative learning, AI alignment, but also in other areas such as like blockchains and decentralized systems. Anyway, so that's all I wanted to say about research today. A quick sort of flash on like some courses that I'm interested in teaching, and I'm like really looking forward to working with like students and like mentoring the next generation. And with that, I will wrap up by saying that incentives are like important and are imperative now. And this has led to a really active interdisciplinary area involving theoretical computer science, AI, and economics, and has been like recognized with a lot of awards recently. And I really want to also point out that like the particular like sort of goal of like looking at the role of information in algorithmic economics has been getting a lot of recent attention from like different perspectives, with a lot of workshops and tutorials being organized, including one that I organized in EC last year. And I'm excited to continue like driving and contributing to tackling these problems. Yeah, so thank you so much for listening. Let me know if you have any questions.
Questions? I had a question. So how do you model in the other setting, in the submodular setting, even the valuation function is unknown, nothing is known. So how do you capture why is it submodular and not sub-iterative? Is there a reason why it's just...
like there is no such an intuitive reason that I can tell you. Like we need submodularity to end up providing some approximation guarantees, basically. So there like the main challenge is like I need to also, so you get to lie both about your valuation functions and signals. So this means that like if my
Wait, sorry. Do you say your function or do you just say the evaluation of...
Good. So so you can think of it. So knowing the function is good, but if you don't want to deal with that, so the way I will like our algorithm will work is that I will elucidate everybody's signals, and I'm going to ask n queries about your for each agent. I'm going to ask n queries, which is going to be here is all the signals. What is your value? So you're going to tell me your value, and then I'm going to be like, okay, here is n-1 signals. What is your value? Like I'm going to do this for every subset of n-1, basically without everything. So each agent needs to tell me n different values, and using this, we will design a thing that is truthful. So the fact that it is subadditive is not going to hurt truthfulness. The fact that it is subadditive won't be able to guarantee that my algorithm gets good approximation guarantees. That's the problem. Yeah.
So you need a signal and you need query access.
I need signal and query access. Yeah.
Other questions? Yeah, let's try again.
Yes. Let me get out of here.